Hello students, welcome back. We just completed sections 4 and 5. Now let's go to section 6, Euclidean Algorithm. The Euclidean algorithm is an algorithmic method to find the GCD. Given pair of integers a and b, we can conduct the division a divided by b to get this expression here. Q is the remainder, Q is the quotient, and R is the remainder. Then the GCD of the original pair, A and B, is the same as the GCD of B and R. And here, remember this, R is the remainder, so R is always greater than or equal to 0 and less than B. And then typically we must have begun with A even bigger than B. So what do we have? Compared with this pair of integers, we got smaller pair of integers, so the GCD computation got easier. And then if still too big, then you can apply this Euclidean algorithm over and over again until you get to the final stage when you have divisibility. Before proving it, let's do an example problem at least once to find out how things are going. Here's the first problem. Find the GCD of 414 and 662, and then express it as a linear combination of those, well, that can wait. And same goes over there. Yes, we'll do those, but those can wait. How can you handle the GCD computation like this? Well, one way to do that is to use the prime factorization. It's an even number, so divide by 2, and then we have 207, that's an odd number, so no more 2. And then they add up to 9, 2 plus 7 is 9, so divisible by 9, so divide by 9, what's left is 23, a prime number. 662 is an even number, divide by 2, we get 331, and it turns out that's a prime number, and it's not easy to check, but here we go, we have the prime factorization, and the common factor. That's how you get the GCD. That's one way to do it. The reason it worked out just fine here is because the numbers are small, just 3-digit numbers, so prime factorization worked out great. In many circumstances, however, instead of 3-digit numbers, what if we have 30-digit numbers or 300-digit numbers? If we have 300-digit numbers, the prime factorization can take even more than the lifetime of the universe, even with the best computers we have. So this prime factorization method just doesn't work for sufficiently large numbers. What we want is an alternative method, which we're going to study here, the Euclidean algorithm. So how does it work? Let's begin with the division algorithm. 662 is bigger number, so divide that by 414. So what's the quotient? And what's the remainder? 4 times 2 is already 8, so quotient has to be 1. And then the remainder will be the subtraction. 6 minus 4, so we have 248. Is that right? Okay, all right. So this GCD computation, let's write 662414, larger number first, so that we have appropriate reduction. So that's what we have so far. It's a step up because numbers got smaller, but still too big. So let's do it again. Divide 414 by some quotient times 248 plus the remainder, like this. The division algorithm. Let's see. 2 times 2 is 4, times 4, 8. Okay, 2 is still too big, so quotient is still 1. And the remainder is I'm getting tired of this, so instead of doing mental math, let me cheat. So we got that. So what does that mean? We got up to here. Okay, 2 steps up. Compared with these, we got much smaller number, but still too big. So let's have another division. 248 divided by 166. What is the quotient? And then what is the remainder? Multiply by 2 and then 320 something. It's still too big, so quotient is still 1. And the remainder will be 166. No, 248 minus 166 is 82. Yeah, in Euclid's time, people used to do this with just mental math or traditional computation, but we can cheat a little bit. Oh, by the way, I have to mark where we are right now. So 166, 82, that's where we are right now. Compared with the original, we got down quite a bit. Okay, still some more thing to do. So make another division. 166 is the quotient, some quotient, remainder, like this. So multiply by 2, then 164. So we get remainder 2, and that's it, I guess. That's a prime number, so we cannot go down any further. But just for an argument's sake, let's write one more. 82 is 41 times 2 plus 0. Okay, we have divisibility, so 2 divides 82. So the GCD of 82 and 2 is going to be 2. So this got down to GCD of 82 and 2. And we have divisibility, so we get this computation. This kind of thing is called Euclidean algorithm. Here we have order quotients, but quotients do not really contribute in the end. Dividend is reduced to divisor and remainder, so it got smaller. So divisor and remainder, that's divisor and remainder. That's how we got smaller, smaller, smaller. The quotients do not contribute in the end. At least not yet. This kind of computation can be done relatively quickly, even for large numbers with humongous number of digits, if you use computers. So this is a kind of thing that computers nowadays do the GCD computation. Of course, if you use computer algebra system like this, then you can find out the GCD right away. But if a problem asks you to do this through Euclidean algorithm, then you have to do it this way, and then you have to show all the work. Work, I mean by these. And then by setting up all those, you may have to do some handheld calculator computation. That's okay. I mean, it's not like Euclid's time, 3,000 years ago. We have another example problem like that, but that can wait. That can wait. Let's go ahead and prove it. I don't know if I have enough time to prove it. So let's postpone the proof. Let's go back to the example problem, and let's go ahead and do this problem. Find out the GCD of 693 and 882 through Euclidean algorithm. Yes, you can do it with the prime factorization. In this case, GCD will turn out to be 63. But you can apply Euclidean algorithm. Let's see. How can you do that? So 882 divided by something, 693 plus the remainder, that's the structure, isn't it? And then Q is certainly 1. And then 189. And the remainder is 1. Okay, 693 is some quotient. That's 189 plus the remainder. And what is this? 693 divided by 189, 3 point something, so quotient is 3. Do this computation, I'm going to get 126. So 693 times quotient times, it's okay. Next, I need 189 is some quotient times 126 plus the remainder. And then multiply by 2, still too big, so quotient is 1. So I'm going to get 189 minus 126, that's 63. And then okay, alright, 126 is equal to some quotient, 63 plus the remainder. Let's see, 126, divided by 63. Oh, we are 2. So quotient is 2, and no more remainder. We have divisibility. So the 63 here is the answer, the GCD. We saw that before in the prime factorization. And of course, here in my notebook, I have all the solution here as well. There are more in homework problems, and please practice those. There will be some exam problems like those, but that's only half the story. The more important half was not discussed yet. That's Bezout's linear combination expression. Excuse me. Let's go back. The second part, and express it as a linear combination of blah blah blah. This part here. This part here. The bigger half still remains, but we don't have enough time. So let's stop here and let's come back and prove Euclidean algorithm. And then let's go ahead and do this further computation with Bezout's linear combination expression. Stay tuned. We are doing some long topic here. Please be patient.